So welcome to another class about the Branch spaces. And today we'll be talking about bounded type. So in the last class, we talked about the Poya class P, which was functions in the upper half plane, not entire functions, entire functions E of Z with certain properties. They don't have any zeros here in the upper half plane, no zeros here. So here is no zeros. And we have a certain, so there are two conditions which could be compressed in just one. But the two conditions were, if you take a point here and then you take its reflection, then E of Z here and E of Z hat, E of Z bar, then we have that the moduli in here is greater than the moduli there. So greater or equal than this. Great, that was one condition, and the other condition was that when you go in a vertical line up, E of x plus iy is non-decreasing. Okay, that was the third condition. So that was the Poya class. If you go in the literature and look for it, people usually use the Poya-Laguerre class or the Laguerre-Poya class, which is often denoted by this LP, Laguerre-Poya class, which is exactly just the Poya class, but then you just require that E has only real zeros, okay. Real. That's the Laguerre-Poya class. If you go in the literature or papers, people usually work with this class rather than only zero and no zeros in the upper half plane. Usually people here also require that E is real in the sense that E Z bar equals E of Z. Usually people also ask this, which means that E of X is real if X is real. This is just a side comment. We won't be dealing with this class for now, maybe in the future, but just for you guys to know that these are the main things that people look. Okay, today we'll be talking about a different kind of class, and this is the bounded type function. So let me make a definition first. So so any function, so you give me an analytic function, say f from some region omega to the complex plane, and then we say that is of bounded type. If you can write this function f as a quotient, okay, and P and Q are analytic functions and bounded. Okay. So for now, I'm defining it in a way that, well, Q could have zeros in there. But if that's the case, then by the fact that F is analytic, that would mean that P has a zero at the same spot with multiplicity greater or equal. Okay, so that's the definition. So whenever, another way of saying that is there is a bounded analytic function Q such that when you multiply Q by F, that function is also bounded in analytic. Okay, so another way, maybe a better way, is saying that there is Q bounded in analytic so that QF, which would be the P, is also bounded. The fact it would be analytic because the product of two analytic functions would be analytic anyway. Okay, so this is another way of saying that. Okay, so this is the class we want to study now, and in the next class we will write what's called the Nevalina factorization, I guess. On the type, and the next class, yes, Nevalina's factorization, which classifies functions which are bounded type in the upper half plane. So we will have a explicit formula for what they should look like. And today we will prepare for that factorization. So what I will do today is, before we start, I will have to solve some problems so I can present the main theorem of today. But before that, I can already pass the problems of this week. So problems. These should be problems 11, 12, 13, 16, 17, 19, and 24. So you perhaps are seeing we have like 7 problems, but really these first 3 problems are really just one problem, which is problem 13, which is the goal, and 11, 12, which is preparations for 13. So basically you just have one problem and then plus 4. So basically you have like 5 problems to do. And these are supposed to be so these 2, again, you have 2 weeks for these ones. Okay, so before we start, I want to solve some problems. So I want to solve problem 20. So what's problem 20 about? Oh, first of all, let me define here bounded type. So we use this symbol for denoting this class, bounded type and of omega. And what's the upper half plane? I would just say bounded type, okay? So I would just use BT for BT of the upper half plane. So problem 20 is saying that if, saying that F belongs to bounded type in the upper half plane if the real part of F is greater than or equal to 0 on C+. Okay, so great. So these are part of the function classes we study in this class. We know how to characterize a function with this property. If it's continuous up to, if the real part is continuous up to the, well, it doesn't need to be continuous. Whenever you have something like this, we have Poisson representation. And these are functions of bounded type. So how do we show that? Well, maybe it's best to prove the follow problem before, which is problem 21, which is BT is closed by sum and product. If you add two functions of bounded type, still bounded type. If you take a product, still a bounded type. And why that is true? Well, if you think about it, it's simple. Like if you add two fractions, then you write this. This is just one fraction, and you see that the numerator and denominator are both bounded functions. And the same as the product, which is even more simple. Okay, so this one is almost obvious. So then now we can solve problem 20. Well, maybe before solving problem 20, let me write the other problem I want to solve, which is problem 22, which is polynomials are contained in bounded type. And the other problem I want to solve, well, the other 23, I want to solve one more, which is problem 23, but that's for later. Okay, so let me solve problem 20. Okay, 21 is solved. Now 20, well, if I want to show that f is of bounded type, I could show just that 1 plus f is of bounded type because bounded type is closed by addition, and definitely the function constant equal 1 is of bounded type. Any bounded function should be a bounded type. Therefore, I just need to show that 1 plus f belongs to bounded type, but then I just write 1 plus f as 1 divided by 1 plus f. Okay, so then my p here is 1, and my q here is 1 divided by 1 plus f. Okay, is p bounded? Of course, yes. Is q bounded? Well, definitely, because the norm of q is definitely less or equal than 1 divided by the moduli of the real part of 1 plus f. Because, well, norm of q will be equal to 1 divided by norm of 1 plus f, which is bound from below by the real part, the moduli of the real part. But this is positive and always greater or equal than 1 because real part of f is greater or equal than 0. So that's actually less or equal than 1. Okay, so p is less or equal than 1, q is less or equal than 1. So therefore, this finishes. Okay, then let's solve 22. For polynomials, well, we only need to show that z belongs to bounded type, the function equal to just z. Because then any monomial, which would just be a product of a bunch of linear functions, will belong to that because bounded type is closed by sum, by product. And then any polynomial will be there. So we just need to show that z belongs to there. Well, but then we only need to show that, say, minus iz belongs to there, because if minus iz belongs to there, therefore z belongs to there, to bounded type. But minus iz belongs to bounded type, that's the question. Well, definitely, because the real part of minus iz in the upper half plane is just y, which is greater or equal than 0. It would just show that this has to be true. So therefore, so yes. And this is by problem 20. This is one way of showing that, and there are other ways. Any questions here in these solutions? Okay, so let me move to problem 23. And this would be more important. So let Zn be a sequence of points in the upper half plane, say Zn equals xn plus I, yn always positive, and assume a certain convergence condition, which looks like just half of the condition for Poya class. In the Poya class, we had 1 plus yn on the denominator. And assume that this condition holds. Okay, then the Blasek product, which we define now, P of z to be 1 minus z over. So we'll put those zn as zeros of this function. And to make it converge, I will have to divide by this function. So this would have poles at zn bar, but I'm just looking at this function b as a function in the upper half plane. So therefore, I have no problems a priori there. But the product, I will show that the product will converge. Then the Blasek product satisfies one, well, it converges uniformly in compact sets of C plus to, C plus, actually, I will look at the function in C plus, but you have even more. You can just, well, if you just avoid the singularities here, then it should be good. And so let me state here. So compact sets of this open set, that means that I'm always at a certain positive distance from this set. 2 and 3 okay, so this is what is called also in the literature. It can it's not it's an inner function called the inner function. An inner function usually in a certain domain is a function which is less or equal than 1 inside, and at the boundary of the domain equals 1. Okay, so usually inner functions have, you can split them into a Blasek product if you remove all the zeros. Plus times some other thing, which we will see in a moment. But if you search in the literature, Blasek products are used to decompose inner functions, okay, which are functions with these two properties here at the boundary. This thing here is, you can show is equivalent of saying the p of x in modulo I equals 1 for all x real. So if you have these two products, yeah. Any questions here in the definition and the problem?
I have a question.
Yeah.
So in the book, everything is always stated about just bounded sets.
Yes.
And I mean, how do we get from compact sets to all bounded sets? So we just take a compact set which is a bit larger and then it works?
No, it's just that, well, usually the topology, in topology sense, the only thing that makes sense is to take uniform convergence on compact sets. It just turns out that in this theory, basically everything works if you replace compact sets by just bounded sets, which would be sets which are like pre-compact in a way, because if you take the closure, they will be compact because they're bounded. But anyway, I'm just used to use the correct terminology for topology wise, but you would see by the proof that there is no argument like procedure like taking, let's say, the limit of points in this set. Just pick one point in that set and you conclude a bound, and you see that the bound works as long as the set is at the positive distance from a certain set you want to avoid. In this case, this guy here.
Okay.
Yeah, you're welcome. Okay. Okay, so let me prove this problem. Okay. So let me show first 2 and 3. These are the easier ones. Well, 2 is really like just observation, really. Because if you take, okay, I have to define what's B star first. So I'm just used to it. So B star here, let me define. It's just, and we will use this star notation throughout the whole class. Okay, so you just take bar in the variable and then you take bar and the function. So that will give you another analytic function because you're doing a double bar. If you think about in terms of power series, if you expand this function as a power series at the origin, the only thing you're doing is you're taking the conjugate of the coefficients in the Taylor expansion. So therefore it will still be analytic. Okay, and then so if you do that, you realize by this formula that the only thing that would change when you take bar in Z and then bar and everything is that this bar here will move to this guy, and so this will vanish, and then we have a bar here. But that would be exactly as just 1 over B. So then B star would be exactly just 1 over B, which is exactly 2. Okay, so that is just an observation. And so 2 is okay. So 2 is trivial. Now 3 is just a calculation, really. If you just take one term, let's say compute the norm squared, that would be, let's just compute it explicitly. And so you recall that these points are in the upper half plane, which yn is positive. So this guy is positive, and this guy here is negative. And then already by this form, you can figure out that this thing has to be less than 1. If you want to really prove it, just multiply both sides. You just multiply both sides by this. This will cancel with that. The squares of the y's will cancel. The squares of the y's will cancel. And then you will have something which is satisfies technical. So this is always less than 1 as long as y is positive. Yeah, so in fact, this is strictly less than 1. So you can even put strictly less. They only equal, they can be equal if you have only zeros in the imaginary axis. All the no, sorry. If you have only real, but you can't have real zeros. The yn's are always positive. Yeah, so it's always less than 1. Okay. Great. So let me show 1. So 1, we have to work a little bit more. Okay, so the first thing we use, we use the inequality 1 plus x, so that's equal to the x for x greater or equal than 0, which is kind of obvious. And then we will use that in the following way. So this guy here would be my x. So we just do that less or equal than the exponential of. Okay. Okay. Then we open this computation. And this would be exactly equal to 1 over z minus 1 over z in bar. And then here we have exactly the thing we claimed, the term which we claimed the sum converges. Great, so you can do one more thing. You can say that this is less or equal than the exponential of, say, 2 over delta, and then this guy. And then this happens if 1 over z minus 1 over z n bar is always greater or equal than delta, which is the same to say that this would be implied if delta is sufficiently small, of course, if z belongs to a certain compact set K contained in this. Okay. Another way of saying if z is at the positive distance from the set of the conjugate of the zeros. Okay. Which is what we want because that's the claim of the problem. Great. So we have an estimate for this term. And why do the hell we want an estimate for this term? It's because we're going to apply problem 8. So what's problem 8? So problem 8 says that 1 plus AB minus 1 is less or equal than a product when A and B can be any two complex numbers. That's a nice inequality because you can iterate it. And probably you use this iteration in another problem. Okay, clearly the second part here, let's say this guy, is in the same shape of this thing. Okay, so if you had like ABC here, then you have a C here, then you could iterate this part one more time, and then you will split the B and the C. Okay, so it's easy to show by induction that this thing is less or equal than the product from j equals 1 to n of 1 plus aj minus 1 mod. Okay. So now we can define bn of z product from j equals 1 to n 1 minus z over zn and 1 minus z over zn bar. And I want to show that these guys converge uniformly in sets which are a positive distance from the conjugate of the zeros. That's what we want to show. Okay, so what we want to measure is this. If I take an R, if let's say R is greater than N, then I want to show that as long as we have this inequality here, this thing, if R and N is sufficiently large, is small. Okay, then what we do is, since R is greater than N, we can split this thing because we have two products and one goes farther than the other. So you can split this thing in 2 bits to N. And then you have another bit, which is J from N plus 1 to R. And then we have a minus 1. Okay, great. Now, what we're going to do is the following. Now we have here the shape of this little result that I put here. Maybe I should do this. Do this. Oh, that looks ugly. I'll leave it. So we have this little result here, and so let's apply it. So then we have the first product here, which I would just denote by these 3 dots. And we have a second problem, which is this guy. So then I'm applying the lemma. Well, and I will have to move this 1 to the right because I just have this thing on this right-hand side. So I will have product from J equals N plus 1 to R of 1 plus, and then moduli 1 minus Z over Zj, 1 minus Z over Zj bar, minus 1 moduli, close this, and then I have a minus 1, and I close this. Okay. Yeah, it looks correct. And now, great. So what else? What else we're gonna do? So this is in almost the shape to apply this little inequality here that I put in the beginning, that 1 plus a term like this loses to something like that. Okay, I could directly apply this to each term here, and I will get a product of these exponentials, so we'll get a sum. That would be great, but I still have to deal with this term here, which is this guy there. Okay, and I have to put in a way that resembles this term again. Okay, and the best way of doing this is just by saying that this thing is less or equal than. Now we write explicitly this term, and I could simply bound it by 1 plus this was the first term, and then we had the second here in brackets, product of J equals N plus 1 to R, and then whatever it is in here minus 1. So I'm just repeating these guys here. And why I can do this thing here, because in here I'm just using the moduli of A is less or equal than 1 plus moduli of A minus 1. Okay. And I can do that because, well, I just have A here and I just bound A by this. Okay, so now I have the same shape, and I can take the product of everything. And then when I take the product of everything, I will have the difference of two products. But if I do that first, then I can't bound the second product, but you have a negative sign in front of it. What I have to do is bound it now, because I do know that this thing here is bounded. I can even remove this thing now. I know that each of these terms, this guy here and this product here, is bounded by, each term is bounded by this inequality here. This is less or equal than that. Okay, so then I can go back and just say that this is less or equal than the product from j equals 1 to n. And then here will be exponential of 2 over delta over yj divided by xj squared plus yj squared. And then in here, then I apply the same bound here, j from n plus 1 to r, the exponential of 2 over delta yj xj squared yj squared, and then minus 1. And then I want to take the products, I will have exactly just the exponential, and then this will be a sum from j equals 1 to r. There's a 2 over delta here, and then a yj, then minus. That is great. So we deduce an inequality, which if you look in the book is the hint of the book, which is deduce this inequality. We just did it. Great. So now, well, then you observe that, well, this thing here, when R converges to 0, is a convergent sequence of numbers. Okay, it's converging to, it's actually increasing. It's converging to some limit. So therefore, it's a Cauchy sequence. So therefore, the difference of these two terms is very small when R and N are large. So I could say that this is less or equal than epsilon if N and R are large. Okay, so that would show that the product, the Blasik product, is indeed converging uniformly in sets that are away in the sense of positive distance from these guys. Okay, and they converge nicely and define an analytic function. So this finishes the solution. Any questions here?
Not from my side.
Great. So now I will state the main results of today and we will show it. Okay, so theorem 8. Let f be a function of bounded type in the Hilbert plane, and such that the origin is not a limit of the zeros of f, meaning that the origin is not an accumulation point of the zeros. Another way of saying that the origin does not belong to the closure of the zeros of f in the upper half plane, of course. Okay, so that's the assumption. Then, let's say if we denote the zeros of f by Zn xn plus I yn, let's say yn positive. Then if the zeros are like this, we have the convergence condition. Okay, this is finite. And then we can write F as a Blasek product times the function G, where B is the Blasek product. We know that the Blasek product is bounded by one of the F plane, so therefore definitely is a function of bounded type, where this is a Blasek product and G is of bounded type as well, and no zeros. Okay, so that's the theorem. Basically, we have all the tools to prove it already. It will be very similar to the proof of the factorization of functions of Poier class. Okay, so we can definitely assume that we have infinitely many zeros, because if you only have finitely many, or the Blasek product will converge, obviously, and if I cut a zero, well, since the Blasek product is a function of bounded type and F is of bounded type, if you divide a function of bounded type, you still have a function of bounded type. So therefore G would be a bounded type. So, and G would have no zeros. So that would be easy. So we can assume Cn or infinite is infinite. Well, I'm even assuming here in the condition. So maybe I should say here. Yes. Okay. Great. So we know that there is some function Q, which is analytic in the upper half plane, so that's the definition of bounded type. Q times F, P is bounded. Oh, we should say here as well, Q bounded. Okay, because F is of bounded type. So let me define M equals to sup P of Z, okay? We know that's a finite number. Great. So let me define Bn Z equals these guys okay, and let me define Gn equals F divided by Bn. Okay, so we do know now that Bn is of bounded type and also Gn are functions of bounded type. Okay. So I have to prove the convergence condition. So if I can prove the convergence condition, then I definitely can take the limit of the Bn's. And then I have to work a little bit to show that the G, so the Gn will converge, of course, and because it's just F divided by Pn. And then Gn, I have to show that still is, the limit is still is of bounded type. It will have no zeros because it will have removed all the zeros of F. So the only thing and we need to show is that yes, we have the convergence condition, and still, when we take the limit, the Gn's still belong to the bounded type class. Okay. So the claim, so we claim that QGN is less or equal than M, which is the M is given by P for all N. Okay. So great, if I show this, then the limit, if it exists, the limit of the Gn will satisfy the same thing. So Q is a bounded function, and you just multiply the bounded function by the limit, and that's less or equal than M, so it's bounded. So therefore, the limit of the G's would be bounded, both bounded type as well. So how can we show this? Well, we just realized that, well, note that F is always, by definition, Bn, Gn. And let's say B0 is the product with, let's say I define here B0 as just being 1. So I know that G0 is of bounded type because G0 is just F. So we can assume by induction that Gn is of bounded type. And then I will show, that Gn, that's of bounded type, that's clear. But I can assume by induction that I do satisfy this. So maybe I should say, so QG0 is less or equal than M. Of course, that this is in C+. In C+, because G0 is just F, so assume do not show that the same is satisfied for n plus 1. So if I do QGN plus 1 and evaluate at some point Z, well, this is exactly just Q. By the way, this thing is defined. I just remove one factor. And then in here, I have the correction factor, which will be this one, which will be inverted by the way we defined G. And I know that this is less or equal than M times 1 minus Z over Zn bar, divided by 1 minus Z over Zn. Okay. So what do I know? So this again, I want to apply the Fragment-Lindelof maximum principle. This is something like O of moduli of Z divided by something of O moduli of Z. So therefore, I can definitely apply the Fragment-Lindelof maximum principle to this function. I just have to know how it behaves at certain horizontal lines. So let me assume that, we take like Z equals X plus IY, and Y I will fix for now as some number H, which, oh, this should be plus 1, of course. So maybe I should go from n minus 1. Yeah, let me assume here n minus 1. So m. So then this would be n, and that this would be n minus 1, and we have Zn here. Now it makes sense. So let me assume that this guy is a number between 0 and yn. Okay, less than yn, but greater than 0. Great. So now I can do this computation here. I can do what is 1 minus z over zn bar divided by 1 minus z over zn. Let's say I do a square. We already did this computation. I would do it fast. This will be exactly equal to what? 1 over 4y yn divided by x minus xn squared plus, yes, y minus yn squared. Okay, so if I want to maximize this in terms of x, I just take x equals xn, so this would definitely be less or equal than if I just cut this part, and if you just rearrange the terms, what you will get is exactly y plus yn, h plus yn and h minus, oh, sorry, let me write it in another way. Yn plus h divided by yn minus h. Great. So I know that this terms is now bounded in this line, and it's bounded. So this function here, which will be less or equal than m times this guy, and this guy is less or equal than this. So I conclude that this function here is bounded by some constant in the line y equals h. And that constant would be this m times the square root of this. Therefore, by the fragment Lindelof maximum principle, which will be theorem 1, I guess, we conclude that QG n of z e moduli is less or equal than m times the square root of for all y greater equal to h. Okay, any questions here? I'm just applying it fast, okay? But that's what it says. If you have a function which has like a polynomial behavior, great, I can always apply it. I just have to know what's the maximum on the line. And so if I compute the maximum on the line, then the function has to be bounded by that number above that line, and that's what we did. Okay, but then h could be any number between 0 and yn. So if I send h to 0, we conclude that QGN is less or equal than m in C++. Okay, so great. So I do have that. Now we just need to show that we can take the convergence of the Blaschke product, and that would finish. If I have that, then Gn converges, the limit will also belong to bounded type because of this inequality. Okay, so how do we do that? And then we use the, so now we know that QF is what? Is Q Bn Gn. Great. So in particular, we know that QF in moduli is less or equal than what? The moduli, oh, sorry, M, because we know the QGN is always less or equal than M times the moduli of Bn. Okay, so let's take the log on both sides. Take the minus log. So this would be greater or equal, when you take the minus log here, basically on the right hand side, I just reverse, take 1 over b, which would just reverse these guys here. So if you do the computation, what you get is what we have have to take the minus log of m, of course, and then plus the sum j equals 1 to n of the log of 1 minus z over zj bar divided by 1 minus z over zj. Yes, we just did that computation right here. Okay, so if I use that, I will have minus log of m plus a half, and then sum of j equals 1 to n of the log of 1 plus, yes, 1 plus, and in here I will make even a better thing. I will put z equals iy. Okay, so x equals 0 in this last identity. So to even simplify more this stuff here, so then we will get what? 4y by n divided by xn squared plus y minus yj. Yes, yj squared. I mean, this is supposed to be y. Correct. Yes. Okay, so what do we have is the following. So now this thing, so now you have to notice something. You have to note that, well, is this true? Is this inequality make sense? Well, this could be a 0. If this is a 0, then this is minus, this is plus infinity. This whole thing. And this bound here is garbage. But this cannot be 0 for y, for every y, because this function here is not identically 0. So if I take y small, there will be a bunch of them that I can put here, and this will give me a finite number. Okay, so I'll just pick one of these y's, which are positive but is small. And how is small? Is small enough so that I can, well, this is positive. So it's small enough so that yes, so recall that log of x would be greater or equal than, say, 1 plus, let's say, x over 2 if, let's say, x, oh, sorry, this is supposed to be 1. If x, let's say, is between 1 and some 1 plus some delta 0, which you can compute the delta 0 is plus 3. Okay. And what happens is, so if y is small, this fraction here will be small. So then I can lower bound this. So minus log of qf of z is greater or equal than minus log of m plus, was that right? No, there is no 1 here, sorry. It's just x over 2. If x is 0, then log is 0, yes. So we can just bound this by, let's say, 1/4. But then we have a 4 there. So it's just y, yn, this will be a sum. J equals 1 to n, yj divided by x. Oh, I keep writing x, n, xj. Xj squared plus y minus yj squared. Okay, and then what you can do is you can realize, well, we do know that the 0 is not an accumulation of points, so maybe I do something here. we do know that that's an assumption that the zero, the origin is not an accumulation of the zeros. Therefore, we do know that, let's say, xj squared plus yj squared is always greater or equal than some delta squared, for instance. So in particular, yes, in particular, if say, let's say 0 is less than y and is less than, let's say, delta, then xj squared plus, say, yes, y minus yj squared, you can show that this is less or equal than, say, 3 xj squared plus yj squared. Because you're going to have a y squared here multiplying, and y is less than delta, and y squared is less than delta squared. If you open this thing, you're going to have some y squared, which is less than delta squared, and the delta squared is less than this. So you definitely can do that. So maybe, okay. So in particular, what you can do is you can go into this inequality here, and then you can replace this bit by something larger. So then making this smaller. Yes. Yeah, because it would be closer to 0, yes. So making this smaller, so you replace by this below for y small, and once we have this log of 1 plus this thing is small, then you have just this y here on the top. And therefore, if y is small, since we have this lower bound here, and this sequence that will be here converges, so this is also uniformly bounded. So then you can guarantee that this thing is small when y is small, okay? So maybe what you should do, maybe I could even complement this thing here. Then what you should do is that 4yj divided by xj squared plus y minus yj squared would be less or equal to, let's say, the 4/3. Oh, we have a y here. 4/3 of y, and then yj divided by xj, oh no, greater or equal, sorry. Yj squared plus yj squared. But then we know that this bit converges, so therefore this is a bounded sequence, okay? So therefore, if y is small, you guarantee that this whole bit is small. And then when you take the log of 1 plus this quantity, this will be reversed, because then you're adding something that's closer to 0. So this will be reversed. And this will be reversed. Be closer to 0. I want something smaller. Yes. So I increase this and I have something smaller. Yes, this too. Yes. This, sorry, then you just take the log of 1 plus this, and then the log of 1. So for a moment, it got confused. So when you take the log of 1 plus this guy, would be greater or equal than the log of 1 plus this guy. Okay. And then now you can do this whole bit here. Okay. So let me, yeah, so we're gonna use this. So maybe I should put it like this. And so now we're gonna have some kind of a constant here. J squared. and a y here. Okay, by all this discussion that I just did. Okay, so now you fix y. So this would work for y is small, for some y is small, as long as this is not 0. Then what you just do is that you select one of these y's and you fix. So, but then the right-hand side works for any n and just take n to infinity. So just fix y small so that qf of iy is not 0, and so that this inequality works. I take n to infinity, so then we conclude that it's finite. Okay, and that would finish the proof. So Bn converges to B, and then Gn will converge to G, and we still would have that this is less or equal than C plus. In C plus, so G is of bounded type and has no zeros. And since Fn is Bn times Gn, this will converge to B times G. And then that finishes the proof. Okay. So any questions in the proof?
I have a question.
Yes.
If you could scroll a little bit higher.
Yeah.
Yes, there. So on the last equation on the page. So there you just set z to be iy.
Yeah.
But I thought that we start with that we want to show this for all z, or do we just need it for just any z, and then?
Oh yeah. So you could just use this identity here for y equals h. Just replace it here. So we would have something like x minus xj squared in here. That would still be true, that whole inequality.
Mm-hmm.
But I just want to extract from this inequality some information, that information being the convergence.
Okay, so we don't care about all z, we just wanted to use it for the bound.
Yes, just wanted to use for the bound. So usually, for these kind of situations in these things, you usually just pick something in the imaginary axis, and as we did before. And before we had something, we couldn't take y equals 0, could take x equals 0. But if we take y equals 1, and then we would realize that that would be enough.
Okay.
Any other questions? Great. So this finishes the proof, and this finishes the class of today. I won't start the next one already because it's more technical. And I do recommend that you at least try to solve problem 24 for next class, which will be more or less important, but not that important. What else? And then on Tuesday, next Tuesday, we will start having more complicated problems. There is one of these problems that is pretty difficult, but I don't remember the exact number. Anyway, if you don't have any more questions there, I will stop the recording. Great, thank you.